Welcome to another exciting lecture. Today we'll be covering welds, repairs, additive manufacturing, and structural optimization. All these topics will be covered at a very top level. Let's start with welds. So the welds is really the processing of joining two metal pieces by heating with or without a feeder material or pressure. The Egyptians had already recognized this approach for welding copper and gold. In 1990s, the welding automation took place using robotics, and you will see that the American Welding Society specifies welds on machine drawings. Here's a circle with this symbol, and that represents a fillet that goes around the circumference, as an example. In general, materials fail in shear due to distortion. And so the criteria for failure is ductile, then it's going to be a shear strength of about half tensile strength. And if it's brittle failure, it's going to be about 3/4 of the tensile strength. Weld analysis is typically based on using the shear strength criteria. Let me cover some ideas about throat here. So presume that you have a weld that connects this flange to this base. And so in this scenario, the throat is the distance from this point to that point. You could have also a weld where it has excess material, but typically you want to define a throat with a minimum amount of material from the point it connects here at the base to the point that connects here at the top of this stiffening element. If you have a concave type of situation, again, you want to be conservative and then select the throat to be this much. Don't account for this extra thickness here. If you have a deep penetration situation, then you're going to consider the throat from here all the way to the deepest location of the penetration of that weld. We call this the throat area. And again, if you have unequal legs, then again, perpendicular from this point to this line, that'll be the throat. Again, if you have a convex type situation, draw point here, and then perpendicular to this plane is what you define throat. And then if you have a concave situation, draw, again, a tangent, and then select the line perpendicular to it. So basically, you want to really be conservative in the throat area definition because that's later used in your weld analysis. Let's talk about stress considerations in welds. So try to really minimize the stresses in the welds. And what you want to do is make the pairing materials carry the highest stresses, not the weld itself. Butt welds are the most efficient. Try to avoid stress concentrations whenever possible. The intermittent weld length should be at least 3 to 5 times the fillet size. So keep that in mind in your designs. Minimize weld size to reduce the potential for fatigue failure. So if you have a weld that has significant amount of welding that covers a large area, that gives you more opportunity for porosity, situations where a crack can develop within the weld and then result in a failure of the weld. So try to have a compact weld in a compacted area and then go from there. So the stress considerations continues here. The welding really process depends on the alloy and the welding process. In general, cracking is promoted by the stress concentration, a brittle parent material after welding. That's specifically true for lower carbon steels. You also have the hydrogen in the metal could be a problem, or impurities in the metal. Any of those things can actually promote crack and then propagate to failure. Prevent overwelding. So, like I said before, have a compact weld and minimize the number of passes. So be efficient with your passes. The more passes you have, there's more potential for residual stresses to get built in, and then also you have the more propensity for defects within the weld. Place welds near the neutral axis of the part, and the purpose there is to reduce eccentricity which could then could be one of the issues in causing cracking is significant amount of eccentricity. So you want to place them near a neutral axis to reduce that amount of eccentricity. Balance welds around the neutral axis and anticipate shrinkage forces, because when a weld cools down, there'll be shrinking going on. Residual stress relief could be a situation that could be used to mitigate some of these concerns. Here's a weld finite element modeling just to show you top level view what is going on. So here you have the midplane of the attachment. Here you have the midplane of the main plate, and we're welding this piece to this piece. And this is a weld that you may have. So typically you will model the shell representative of this plate. So you only model the mid surface using shell elements. And then for the bottom piece, you could also use shell elements. And the idea there is to connect these pieces with another shell that goes from this point to this point. And the idea there is then to have a mesh density fine enough where, you know, it has enough definition to get a general perspective on the loading that you're getting into this weld. Another point I want to make is when you apply a load and you have a piece that's attached to this base and is welded all around, I want to point out that this weld by itself is going to cause a stress concentration. So far away from this weld, you may have a uniform stress, but as I approach the welded area, you're going to have an increase in weld stress at point A. And also, when I look at the stresses here, you're going to see a high stress at point B as well. Here's another example from the side view. So if I have a load H, a load V, I'm going to have some amount of axial loading, some amount of bending. But when I approach the weld toe plane, and I call this toe where the weld attaches here, then the stress is going to peak in this manner. So this is going to accentuate this stress to this much. I also want to point out that there are two different weld configurations as an example. Here's a butt weld because you have two pieces that are connected through a butt weld. So these two pieces are coming separately into this butt weld. You also have a T-joint fillet. In this case, you have this piece coming to this base with a weld on this corner and this corner. The size of the weld matters. So for example, we talked about throat area or distance. Here, I have this protrusion of this weld to the outside of this base plate. So what we really want to consider is the throat thickness T1 and not account for this excess material. For the butt weld in this scenario, we want to count T1 here, not T2, which goes from here to here. We want to reconsider T1, which goes from the top of the plate to where the butt weld penetrates to. And so that this T1 here and this T1 here is considered design throat area. You could also have a partial penetration butt weld. In this case, you have some amount of weld here, some amount of weld here, which may not have penetrated all throughout. And so here your design is going to be T1 here, okay, plus T1 prime. You don't want to consider T2 plus T2 prime, but just the minimum thickness possible, not the excess material. And so failure to achieve full penetration can occur. We call this incomplete penetration when this happens. And so it's important to understand that that could happen. And if you don't consider that, you could, for example, assume that is a whole thickness, and it may not be the whole thickness because it's not fully penetrated. So you want to be careful with that and ensure that you have considered the correct design thickness. I also want to now show an example where this element here, this stiffening element, does not carry any loads. In this scenario, the stress path, if I were to have a load on the base, is simply that the load will then go beneath in this manner. So the stress path is going to try to avoid these areas of stress concentration. Sometimes you're going to get a high stress here in the corner, right? But very little stress here at the top. When the stiffening element carries loads, then the stress path will go right through the weld to the top member, or vice versa. I want to show you a little bit about how these analyses can be conducted using hand calculations as an example. So I have the loading here, shear load here, and in this example, I should get a reaction force just like that. And so now I'm going to consider a plane within this weld. This plane is going to have two tangential shear loads to that plane in purple and a normal stress to that plane. And so the normal stress to that plane is simply P times cosine alpha, where alpha is the angle of the fillet, and we're going to divide that by A. And A here is T times cosine alpha. We also have to define the shears and tau 2. After you calculate this, you get a resultant equivalent stress. Now this R here is a shear load in this direction, and the area we're talking about is this purple one here. There's also a mistake. This should be T divided by cosine alpha. Some more welding symbol examples. So here I have a weld leg size of 5 millimeters. We have a fitted weld, and I know that from this symbol, and it's on both sides. That's why I have this triangle. If I go here in this example, here I have a single triangle because I only have a weld on one side. When you see a symbol like that, it means that I have an intermittent weld and that it is staggered at 60 millimeters along on 200 millimeter centers. So this is what this means. And then I already covered this example earlier, so we can keep going here. The circle indicates that the weld goes all around. Here I have more examples. So here I have two parallels here. That's a butt joint. Here I have a surface that's butt joint, but is slanted and at 60 degrees. So that will mean that it's at 60 degrees. This gives me the distance, and then that tells me this triangle, this angled means that it's slanted on both ends, and this is considered a butt joint. Here I have a situation where it's also butt joint, and it just means that it comes in with a double slanted surface in this manner. And then here, this symbol here represents one side is slanted and not the other. Here's more examples. So here I have a weld on both ends, and this means that I have a slanted surface on both ends, like I discussed before. This symbol represents that the penetration of that weld is now throughout. It's not all the way through. While this one represents that the weld only affects mostly affects on one of the sides of the joint. It's still a butt weld though. And then here I have a butt joint. That's the ones like I showed here. So that's just another example. Let's discuss. So here we have a simple butt joint loaded in tension. It can be in compression, and then this here could be loaded in shear. And so throat H does not include the extra reinforcement as discussed. So the design throat thickness goes from here to here. The reinforcement does add some strength for static loaded joints, but it could be a problem for fatigue. So you may want to pay attention to that. Here L is the length of the weld, and so clearly the stress in this consideration is the force divided by this length and times this thickness here, H. So that's the formula, and that happens to be the formula also if I were work to apply shear. If I have a transverse fillet weld, and a transverse fillet weld looks like this one right here, I have a load apply F, and that gets reacted by 2F. I want to look at this here. That's the throat here in this case. Recall, from here to here, that's your miter weld. And so I'm going to draw this carefully here. I've not drawn the whole triangle, but I cut through at some angle to study the shear stresses within this weld. I have a normal stress or normal force to that plane. So it's a cut, arbitrary cut, right through the weld. I'm only showing the top here. And an angle theta here, and presume this 45 degrees per second. This is your T there that we discussed earlier, okay? So I'm examining these forces relative to this F, and that's simply a summation of forces. So Fs equals F sine theta, Fn equals F cosine theta. So I'm taking this F and then finding the components, the resultants of that in this plane. And so I can use some trigonometry to relate this thickness H to this theta and this throat, design throat. So that should be fairly simple. H is known, and then the throat is known. So you can calculate theta. And then the nominal stresses at an angle theta then become Fs divided by A. And so you can calculate A fairly simply. And then you're going to get this formula for these. So Fs is F sine theta, and then A is all of this, HL over divided by cosine theta plus sine theta. Okay, so what we've done is we've applied this formula right here. And so then, and so again, if I want to calculate the stress, I want to divide this Fs by this area. And this area is given by T times L. And I found T relative to H, and that's why you see here that got this formula. And then I can multiply everything out, and I get this. For this stress, I get this. And then I can use the von Mises stress, calculate the von Mises stress at an angle, which is this right here is the distortion, right? That's what von Mises stress gives, is a distortional stress of some kind. I'll substitute this here, and then this is your von Mises stress, which depends on theta alone now. And so now I can figure out which plane theta I have the worst case stress. Continuing here, when we do the calculation, you will find that the largest von Mises stresses occur at theta equals 62.5. And so that'll give you a value of 2.16 times F divided by HL. And the maximum shear stress will occur about 67 degrees with a value of 1.207 force divided by HL. So two important parameters. No analytical approach really exists to accurately predict the experimental measured stress. So the standard practice is to use the simple conservative models that we're discussing. And we assume that external loads are simply carried entirely by the shear forces on the minimum throat area. And we also sometimes even ignore the normal stress on the throat. The shear stresses are inflated to sufficiently render the model conservative. So that's one approach that people use. This is totally acceptable right here, just trying to explain that the normal stress here tends to be ignored, and then the shear stress tends to be increased to account for that. By comparison with the previous maximum shear stress model, this particular formula overestimates this one by a factor of 1.17. So it's not too different from the one I showed here. 1.41 versus this one right here for the maximum shear stress formula. Parallel fillets can also be treated the same way. Now H is this distance, L is that distance, and then tau is calculated using this formula. And it can be applied. The strength of welded joints. So must check for failure in the parent material and in the weld. The weld strength is dependent on the choice of the material they use as a filler or electrode material. Weld material is often stronger than the parent material, but not always. Sometimes the interface between the weld material and the parent material can be a problem, or sometimes it could be at the heat affected zone, or has. Right where the heat affected zone ends, that can be an area of high gradients relative to what's going on with a structural system. The parent material experiences heat effects near the weld, and that's what I was just discussing now. So resistance welding. So welding by passing electrical current through parts that really press together, that's how that works. Common forms of doing this is spot welding and seam welding. Failure by shear of weld or tearing of the member. And you can also avoid loading the joint in tension to avoid tearing. Two categories for welding processes. You have the fusion welding. It can coalesce by melting two parts to be joined, and in some cases you want to add a filler material to the joint. Examples are just what they want here. The resistance welding is one example. And you have the arc welding and the gas welding. You also have solid state welding. In the cases here, you apply heat and or pressure, and these are achieved, are used to achieve coalescence, but no melting of base materials occurs and no filler metals are added. Examples of this is forge welding, diffusion welding, and friction welding. Let's look at arc welding. So fusion welding process usually coalesce materials by heat from an electric arc. Here's a picture of everything you need. You need a power, AC or DC power source. You need an electrode cable that's fed in, and an electrode holder here. And then here's a consumable or non-consumable electrode. And then you have the feeder material that could be included. And then here you have the material to be worked. And then here you have a clamp that keeps everything together. And here is a solidified weld metal that occurred from the welding process. And here, in this curve right here area, you can see the molten weld metal. The electric energy can produce up to 5,500 degrees C. It can melt any metal at that point. Most arc welding processes and add filler material to increase volume and strength to the weld. Typically, a pool of molten metal is formed near the electrode tip, and as the electrode is moved along the joint, the molten weld pool solidifies just like what you see here. So the problems with the manual welding typically happens to be the weld joint quality and productivity. You also have a technique called gas tungsten arc welding. It does produce high quality welds for a lot of suitable applications. You have no spatter because there's no feeder material metal through the arc, and there's little or no post-weld cleaning because there's no flux. The disadvantage is that you have a slower, most costly than consumable electrode arc welding process. And here you have a shielding gas, okay? In this case, you have a tungsten electrode that's not acting as a feeder in this case. You also have plasma arc welding. It's a special form of the gas tungsten arc welding, in which constricted plasma arc is directed at the weld area. Here you can see the various components. You can see the tungsten electrode, the plasma gas, and then you have again, very similar situation, but now you have a plasma stream. The tungsten electrode is contained in a nozzle that focuses a high velocity stream of inert gas into the arc region to form a high velocity, intensely hot plasma arc stream. The advantages of this approach is that you have good arc stability, excellent weld quality, better penetration control than other arc weld processes. You can actually increase the travel speed of this system and can be used almost in any metal. This disadvantage is expense, and that you need a larger torque size than many other arc weld processing. This tends to restrict the areas where you can work the joints. We also have the resistance welding, spot welding. And so again, what we're discussing here fall on the fusion welding. So I covered arc welding. I'll be talking about resistance spot welding. So a group of fusion welding processes, they use heat and pressure. So apply a force here, you apply a force here, and this is your electrode, and then you have the sheet metal parts to be joined. And so you use a combination of heat and pressure to accomplish this coalescence of the materials. And the heat is generated by the current that's transmitted through the electrode. The heat generated by electrical resistance to the current flow causes things to get welded. So here's an example. You have the electrodes coming in. I have the force applied, and then applies the current, which then heats up, and then you get the molten metal there, and then you get the weld nugget in there. Here's the spot welding cycle. So here's the force. The force, number one, no force. Number two, force is increased, and then force is decreased after this step number 4. And then here, step number 3 is when I apply the current, and sometimes a small current again. So that's your spot welding process. Advantages: no feeder material required, it's clean. High production rates are possible, lends itself to mechanization and automation, lower operator skill level, and then good repetition and reliability. Disadvantages: you can get low strength at times, high initial equipment costs, and limited to lap joints for most of these processes. You also have the idea of the electron beam welding. It's a fusion welding process in which heat from welding is provided by highly focused, highly intense stream of electrons striking the working surface. The electron beam gun operates at high voltage to accelerate electrons, and beam currents are typically low, measured in the milliamps. The advantages: so you have a high quality weld, deep and narrow profiles. It does limit the heat affected zone, and you have low thermal distortion. There's no flux or shielding of gases needed. The disadvantages, again, is the cost. This kind of technology can emit X-ray, which could be a health concern, and a vacuum chamber is required. You also need a lot of preparation and aligning the system to make this work. Friction welding is another approach. Basically, coalescence is achieved by, so now what I'm looking at, just to point to you where we are at, we're here at the bottom, solid state welding. Coalescence is achieved by frictional heat combined with pressure. So here I have in number 1 a rotating part but no contact. Number 2, the parts come into contact and generate friction, and that friction generates heat. And then in step number 3, you then start getting a weld formation. So you stop and you apply pressure again. And then number 4, the weld is created. So the coalescence is really caused by that frictional heat combined with that pressure. And it can be used to join dissimilar materials. This is widely used in commercial processes, in automation, and mass production. The one point I want to make is this is used mostly in shafts that can rotate. The friction stir welding process is a very common process as well. In this case, you have a rotating tool, and that rotating tool is fed along the joint line. So this is a joint line here between 2 working pieces, and then it generates friction, heat, and it mechanically stirs the material to form that weld seam, which is why it's called the friction stir welding. We distinguish this process from this one, the friction welding, because heat is generated by a separate resistance tool rather than the parts themselves. In this case, these are the parts I want to join. I use pressure to combine these materials, but in this case, I'm using an external wear resistance tool. The advantage of this material has been found. They do get great mechanical properties. It avoids the toxic fumes, warping and shielding issues. There's little distortion or shrinkage, and you get a great weld appearance. The disadvantage is that you get a hole when you withdraw the tool. And heavy-duty clamping is required because of the forces that get involved. So the weld quality, weld quality needs to be really strong and needs to be absent of defects. You need to implement methods of inspecting and testing the joint to assure the highest quality. The topics of concerns in weld quality happen to be residual stresses, distortion, welding defects, and then also you want to be able to come up with good inspection and testing methods to demonstrate that the welding process was in fact successful. There's techniques to minimize warpage, welding fixtures to physically restrain the parts, heat sinks to rapidly remove heat so that you don't get the residual stresses that could start moving to the part, tack welding at multiple points to create a rigid structure prior to actually welding for sure, selection of welding conditions such as speed, amount of filler metal used to reduce warpage, and then preheating the base parts, stress heat treatment of welded assemblies, and proper design of weldments. So preheating reduces that stress concentration during the welding process, brings everything closer. When everything cools down together. Welding defects can be a significant problem for welds. You can have cracks, cavities, solid inclusions, which could be stress concentrations, imperfect shapes or unacceptable contours, incomplete fusion, and miscellaneous defects. Here you have a transverse crack, a longitudinal crack, a toe crack, or here you have examples of incomplete fusion. There's two types of defects similar to the defects found in castings. You have porosity, which are small voids in weld metal formed by gases and trapped during solidification. So these voids will contain these voids will be really created by gases entrapped, and it could be, you can have various types of surface contaminants. You could have inclusion of atmospheric gases, sulfur in weld metals. You can have shrinkage of voids, which are basically cavities formed by shrinkage during solidification. There are inspection techniques that can be used for examining these type of welds. Visual inspection is the most widely used inspection method. You'll have a 10x magnification glass with a lighting, and you're looking for dimensions, warpage, cracks, cavities, incomplete fusion. You can really only look at surface defects for the most part. There's nothing more you can check. Limitations really only include surface defects, and the welding inspector must also decide if additional tests are warranted. A non-destructive evaluation is really nice. It provides a view of what's going on inside in the areas where you cannot see, and ultrasonic testing is one way to accomplish that. You have high-frequency sound waves through the specimens to detect cracks and inclusions. You have radiographic testing. X-rays is an example. Dye penetrant can be very useful and can detect small cracks and cavities. And then you have the magnetic particle inspections, which can really help reveal subsurface defects by distorting the magnetic field. You also have destructive testing, but this is really done to really understand how welds are behaving. For example, if you're going to develop a welding process, you may want to develop a bunch of coupons and cut them up to understand how the welding process got implemented and how well it did. Destructive testing is testing where you need to destroy the sample by testing it, of course. Here are some typical testing you can do. You can apply a weld, and the idea is to have a weld similar to what you're going to have in real life, and then pull the load to understand what's going on. Another kind measures is a fitted break test. Basically, you have a T-type joint. You apply the load, and really what you're looking for is how this weld breaks in this configuration. You also have the tension shear type testing, which is really good for spot welds. It gives you a good idea about how spot welds behave, as an example. But you could also have a weld here and a weld here. The idea is to get properties, mechanical properties that you can use for your design. You can also have a situation like this one, which is a peel test for spot welds. In essence, you have a spot weld here, you grab it here, this is the original position, and then you pull it with a peel force. And the idea here is to test that particular weld. This metallurgical test that can be performed, what you want to do is after you do this test, you want to cut it up. And also you may want to have samples that you cut it up before testing. And the idea there is to look for photomicrographs of the welds to examine metallic structure, defects, the extent and condition of the heat affected zone, and similar phenomena. But a lot of this testing can be very helpful to develop coupon allowable data. It can also start giving you an idea about the repetition of a good quality weld. It can actually surface issues with the weld quality in the first place. So this testing, if you repeat it by operators, and you increase the amount of testing that you do, the more you're going to learn about this. And so here we want to look at the weldability, which is what is the capacity of a metal or a combination of metals to be welded into a suitable structure, and for the resulting weld to really possess the required metallurgical properties to perform in a satisfying way in the intended service. So good weldability is characterized by the ease in which the welding is accomplished, the absence of weld defects, and a good strength, good ductility, and toughness in the welded joint. There's also this idea of weldability factor. Some metals or metal combinations can be readily welded by one process, but are difficult to weld by others. So like stainless steel can be easily welded by the arc welding and resistance welding, but could be difficult by other methods. Some metals melt too easily, like aluminum, so may not be conducive to some of those techniques. Metals with high thermal conductivity transfer heat away from the weld, which causes problems. Copper is an example. High thermal expansion and contraction in metals causes distortion and can be an issue. And then dissimilar metals poses problems in welding when physical material properties are quite different. Continuing here, the fitted material must be compatible with the base metals. Surface conditions can be quite important. So if you have a moisture, that can result in porosity, and then oxides and other films can prevent adequate contact and fusion. There's a lot of advanced weld simulations that exist that I think can be used. Some of them are quite complex. Some of them are good top-level types of analyses. When it comes to welds, it's sometimes a good idea to start simple, do a lot of testing, learn about the quality of the welds, and increase your confidence in the allowables. But if you really want to understand what is going on with the weld stresses, with high attention to detail, rather than using a macro approach, which is to basically test welded samples like this and get allowables that can be then applied to a system, that's one way. But if you want to learn more about what the weld is doing, then you need to start looking at weld microstructural modeling, which accounts for phase transformations, grain growth. Then you have a weld thermofluid model, which accounts for heat transfer and mass transfer. You have a weld residual stress model, which is going to incorporate these two areas, and then it's going to model the bead geometry, the material properties, the microstructure, and the thermal induced stresses. You also have the idea of incorporating stress strain curves into the modeling. Weld simulation can also be as complex as incorporating stuff in finite models where you do thermal analyses. You have material subroutines that model a lot of these transformations we're talking about, and then you can determine how residual stress distortions are occurring. And then you can also do structural analysis to incorporate other kinds of loads. One approach to deal with these residual stresses is to account that into your materials allowables. The idea there is that if you do enough testing with the right configuration, you can then determine what the residual stresses are doing to you. So that's another approach that people use. Residual stress predictions can actually be very good with these approaches. Um, and they tend to be pretty high from the weld. So if this is the edge of the weld, the toe, then the stress is going to increase quite significantly towards that edge and then decrease away from it. And here's some more examples of what residual stresses can do with weld pass speeds as an example. So one of the things I want to point out is that welding residual stresses is going to depend upon the number of passes, how quickly you create a weld, and things like that. Weld sequence also matters, so depending upon how you put the weld sequence, here I have an example, 1, 2, 3. So this is 1, then 2, then 3. In this scenario, you'll get some amount of weld stress. But if you did 1, 3, and 2, then you get even lower stresses. And then if you did 1, 2, and 3 in a different way, then you can get higher stresses. So it's important to understand that weld sequence matters. The approach to treat welds is just like composites, I will say. You know, you want to increase confidence in your weld quality by doing a lot of testing. You want to develop coupon test allowables. You know, have a whole mechanics composites course in YouTube. You can check it out. But, you know, I think you need to pay attention to the testing and learn about what your welds are doing to the heat affected zones, where the samples are failing, what kind of residual stresses you're putting in them, and then doing a lot of destructive testing to make sure you have a repetitive quality of that weld, but also looking for porosity, cavities, cracking, and all the things we talked about. These samples can be quite beneficial too. You can inspect the welds. You can learn about how to better inspect them in the field, such as the ultrasonic inspections we talked about, eddy current, or any of the other techniques like X-ray can be used and leveraged to develop acceptance criteria for the welds, where you can attack, you can put flaws on purpose or crack the welds on purpose. Tie that to an acceptance criteria there with an inspection, and then make sure that when you go to the field, that when you apply that inspection, you can repeat the acceptance criteria and judge it against your qualification program, which could be made of hundreds of coupons. A proof test could be a good way also to verify joint quality. We talked about that. And so now I'm going to jump into repairs. There are various kinds of damage in composites that may require repair, which is today's lecture, part of the lecture. Damage detection leads to damage assessment. And so the first step is to really understand why the damage occurred. But the typical types of damage you may encounter is surface damage, delamination, cracking, impact damage, bearing damage, punctures, matrix creasing, bond failure, heat damage, or chemical failures. Damage classification can be either allowable, you're allowed to repair it temporarily, repair is allowed, or is non-repairable. We'll talk about that a little bit later as we go through this lecture. But anytime you have any kind of damage, the first step is to take photographs, assess the situation, and then develop a contingency plan to address these levels of damage. Delaminations are associated with applied waviness sometimes, that can occur. And so as part of the manufacturing, you may not have any type of damage like this. It could be a damage just from manufacturing. You may have to take steps and you may have to bolt something through. Like in this example, there's damage internally due to these wavy patterns, but you can then bolt it and bring everything together, maybe strengthen it. That's one approach. Typical damage that could occur is, for example, impact damage, where at the point of impact you have either localized damage, and then on the underlying surface could be even more damage. So it's important to keep attention on that. That's for monolithic laminates. In a sandwich structure, you're going to get a local amount of damage, but you may get some core crushing. And then here you have a situation where the whole sandwich got punctured in this manner. Laminate splitting can also occur, and it can degrade the mechanical performance relative to the thickness that you may have. Other typical damage is heat damage, a local fracture, which basically forms some sort of blistering. You also have a bolt hole damage, which can occur from drilling the hole, and it could also cause splitting of the composite, as an example. Here's some typical damage from a impact event on a section of a fuselage. Here I have a Boeing 737 that had a hanger damage. All those need to be repaired because you don't want to spend millions of dollars to replace a whole aircraft. If you can replace sections, why not? You have a lightning strike event where also requires an amount of repairing going on in this area. And then you have ground hails causing all this damage, just dents. So in composites, very specifically, you can have a high energy impact event that causes delaminations, damage through the whole panel. You also have a medium amount of energy impact where there's a lot of localized damage, and then you get delaminations and matrix cracking. You can also get some amount of fiber failure in the backside. A low energy impact may not even show anything at the top, but yet cause a lot of delamination and matrix cracking just at the subsurface. Delamination and shear cracks and fiber failures are common types of failures you could have. And here's a situation of drilling, which can cause ply lifting or delamination in this manner. So defects are common in composites and metals. The need for repairs that may not be qualified through full-scale qualification testing may be a reality. So you may not have the ability to be able to demonstrate the repair at the full-scale testing of an airplane, or launch vehicle or spacecraft. So the purpose of the repair is really to restore the composite or the metal back to the structural capability of the qualified state. So if you have qualified something to 10 million pounds or 1 million pounds, you want that repair to also survive those conditions. You want that repair to survive the same loading conditions. So repair of composite materials, you want to restore the form, fit, and function of the structure. Some composites may not be amenable to repair, so you have to think of ways to make that happen. The steps to repair usually involve inspection protocols. It is looking for what kinds of damage modes we're looking for. Is looking at inspection techniques to look for stuff that I'm not aware of because of that damage. So before even implementing a repair, you definitely want to understand what caused the repair, what caused the damage in the first place. Take some corrective actions there. Take pictures of the damage and then discuss that with your manufacturing team and try to get a significant amount of understanding about what drove you to that point. And so this next thing we want to look at is looking at the repairs. And so you have repairs which require safety aspects, making sure you don't have any concerns with health issues. The fibers can cause skin rash, if there's like asbestos particles, resin, like during the sanding process, there could be dust that you aspire, and then there's materials disposal. Personal protection equipment is important, and you also have for aircraft regulations. Consideration for repair of adhesives involves the performance, the service temperature, making sure that the surface preparation techniques are compatible with what you're trying to accomplish. So I invite you to look at the adhesive bonded joint video where I discuss some of that. Um, Porosity of the bond line, tolerance to the mismatch in the thermal coefficient, coefficient of thermal expansion, the outtime of the adhesive, sensitivity to bond line thickness, and cure parameters such as time, pressure, and temperature. So a lot of the things we talked about in the bonded joint lecture apply here. So issues that could occur when you're repairing using adhesive. So you have the autoclave only cure, that's an issue. The equipment may not be available in the field, and so the part may have to be removed and disassembled for repair. You have the press curing, so equipment may not be available for that either. You also have the high temperature cure situation. Um, And so you also have high temperature cure that can be an issue as well. The damage to the surrounding structure in an aircraft, to repair an aircraft, you may need to apply that, and that may not be available, or may be difficult to apply. You have the protective equipment needed to handle high temperatures, and then you may have to figure out ways to um, basically bring all this stuff to the field, and so you need to have a freezer to store the composites. So how are you going to do that? And so that becomes a logistical nightmare potentially. There are some typical repair methods. You may use speed tape, which is, think about it as metallized duct tape. So the aluminum foil with contact adhesive will keep minor dings from getting worse. Resin sealing, so use the resin to capture any loose fibers and prevent damage growth. Potted fibers or repairs, so drill and fill are common for sandwich structures. Doublers could be bolted or bonded, and it can be temporary or permanent. You can pre-made the doublers, and it doesn't require perishable materials. It must be kept in inventory. You must have a bond line control there, and matching ply labs. Cut-cured doublers can also be used. You want to have matching contours, thin bond lines, and optimized repair sizes. And also use the correct layup, because you don't want to use a layup that will cause the patch to come off. The surface prep is important to get a good bond, and it's critical. A wet layup at room temperature is easier to do if you can meet the performance requirements. It doesn't require a lot of tooling, and is usually used on small damage. Elevated temperature repair requires heat and pressure. It's more complex, requires a thermal blanket and a local vacuum applied. Pre-preg can be used. It's easier to work with because you don't have to mix the resin, but cure is also required. Here's some of the equipment that can be used for repairing. You can see here the vacuum bag has been applied, and then you have all this stuff connected to machine after the repair is completed to ensure that you complete the repair fully. Here's another more complicated machine here on the left and on the bottom as well. So here's just some examples of repair procedures. Here's a picture of a doubler repair, quite complex in nature, but in effect, what you see here is a template and how they plan to implement that repair. And in this case, they're trying to complete the repair, and you can see the tape with plastic all around. Type of repairs depends on whether the damage is on a composite laminated structure or a sandwich structure. The damage assessment should be performed with a non-destructive evaluation. We want to basically rule out any subsurface damage, and you need to be able to understand the damage fully um, before you take any action. Um, you also want to make sure that repair should be controlled and not operator dependent, and follow a procedure that has been vetted through analysis and testing. A robust process ensures that the structure is designed for durability and making sure you can repair it. Repairs for composites depends on what we're trying to accomplish. It could be just a cosmetic repair, a structural repair, or a prevention repair, so to arrest the flaw. I'll show some examples later on that one. Few repair methods exist, so you have the bolted patch or the bonded patch. So two approaches there. On the right-hand side, I show more of a bolted patch configuration. Before discussing repairs, I wanted to make sure the types of damage that should be considered. You have the allowable damage that does not require any structural repair. And the next one is you want to make sure, and so again, the allowable damage does not require any structural repair. The damage may not even affect the structural integrity nor decrease the function of the component. A repairable damage is one where the damage exceeds the allowable damage size, but is below the non-repairable damage size. And so the damage leading to strength degradation below ultimate load must be repaired. Non-repairable damage is one where the replacement of the component is required because the damage cannot be substantiated in any way. And so in those cases, you have to replace the component. For bonded repairs, the size limit is really determined by the damage size that can sustain limit loads without repair. And for bolted repairs, it is constrained by how feasible how feasible you can implement such a repair. But again, three types of damage, some of them not repairable, some of them repairable, and some of them don't require any repairs. So something to consider there. Inspection of the flight article is performed using non-destructive techniques after manufacturing, but inspection can also occur after the incident. Typically, the first inspection is visual, and again, you want to take pictures, understand how the damage occurred, understand all the factors that went into the damage. And the purpose of the NDT is to establish the damage extent, delamination growth, under impact conditions or manufacturing-induced flaws. Very important consideration. And so here it is, the damage assessments. Damage to composites may be obvious and easily assessed. Damage to composite can be difficult to assess and may not be obvious. The damage may appear quite small, although the real damage is far greater. Impact damage to fibers can appear as small as a dent, but the underlying damage can be quite extensive. The decision to repair or scrap can be based on ensuring original strength can be restored. And so use as is when the allowable damage is met. Repair is when you exceed the allowable damage, and scrap is when the damage is extensive to repair, too extensive for a repair. Challenges can occur, so you have collateral damage, accessibility constraints, cost, implementation of that repair procedure, and evaluation of the repair can be quite difficult. And it requires analysis and test. And these are not very easy things to address always, especially when you have damage. You know, just imagine you dropped a wrench or a hammer on a critical structure. You know, what are you going to do with the underlying damage? Do you know how deep the damage went in? Do you know how to even analyze it? Do you know how to do non-destructive evaluation to make sure you didn't miss anything? So these are not easy things to really address. NDE measurements of the material characteristic of the damage can provide a lot of information about how the extent of the damage, how deep it went, and so forth. Ultrasound, X-ray, these are different approaches that can be used to inspect the damage. You have visual, So you can look at the surface defects. You can also apply acoustic emission, thermography, radiography, eddy current, microwave, and other techniques that exist in the literature. Most common inspections is to apply a visual inspection first to really look for the damage. It is harder, it's quite difficult to do to find all kinds of damage. You can stay surface. It'll be a surface inspection primarily. But composite presents a lot of difficult issues. The low contrast, because of the black fibers, makes it very difficult to visually inspect. And so you could also have a situation where you may need a borescope inspection, looking for internal parts that may have gotten damaged. Very hard to do. The advantage is that you can record and aid the additional evaluation. But visual inspection is good. You can look for any dents, any surface issues, and so forth. So substantiation, the standards do require to restore the structure to the flight-worthy condition. And so the substantiation of the repair, you want to make sure that you use analysis or test to demonstrate that you actually did that. You're able to recover the original strength. The substantiation of the repairs is usually done by analysis, supported by tests typically. So you can do an analysis, trying to anchor to a test, and then apply it to the actual situation. The repair fulfills the same requirements as the parent structure. The representative damage sizes can be quite important, and so that's important. You really want to apply coupon level testing, even subscale level testing to validate the analysis approaches. You also want to be able to show that the analysis is a good approach to predicting the failure of these repairs accurately. And so you want to do that through extensive testing. We also have methodologies for repairs that are quite important, and FAA has documented a lot of case studies of inadequate bonded repairs that could be quite significant. And so you want to make sure that bonded repairs be designed so that the bond fails between arresting features and the remaining structure can hold the load. You also want to make sure that data supporting the bonded repairs be included in the inspections and that you're capable of detecting complete or partial failure of the bond lines. The bonded repairs should follow standard practices. They should have repair technicians that are trained. You want to make sure the repair design is extremely, good in terms of how you're implementing that. Reverse engineering techniques, and then you also want to make sure that repairs are performed in a controlled environment. Here's what we're talking about, the building block approach, and this is what Airbus will use. You have the coupon level test, then you go into allowable developments, and then you increase the level of complexity until you have high confidence in your designs. The definition of a generic allowable set, so typically you want to generate good allowables, you want to validate your computational models, and then perform a validation of the approach. You need to really understand the failure modes involved, such as delaminations, fiber failure, and core damage. I invite you to look at the Mechanics of Composites lecture where I discuss the failure of composites and the failure modes and the failure criteria that are typically used. The intent is really to restore the strength back to the qualification of that structure. And so analysis comes into play, and so that's why it's so important to understand these failure modes because of that. Bonded arm repairs constitute a discontinuity of the original plies and therefore a stress riser. And so structural repair schemes are normally require extra plies in the repair area. So very important to have a robust repair that restores the strength of the composite. Here, you have a past repair. The area was cut out. It requires very minimal preparation. you cut out and then put the feeder plies, a film adhesive, and on top you'll put the repair plies. And so you definitely want to have a drop off about this length right here, from here to here, about 10 to 15 times the thickness. Very important to keep that in mind. Very careful surface preparation is required for good adhesion, and you need to, really inspect the workmanship. You need to inspect the work to ensure that you have good bonding. And so it's really a good idea to have an extra ply just in case. You want to make sure that the materials are compatible at the interface. You also have other approaches, and these are called a scarf repair, where you remove the plies and then you bond them all. You bond it all together. That allows more surface to be bonded, and the repair is only marginally thicker than the original. Each repair is each repair has a ply that overlaps by another ply, and so that leads to an optimal load path. It reduces eccentricity, and the disadvantage is that you could have potential collateral damage when you sand it out, because you have to sand this stuff out to be able to get these plies to lay down the way that you see here. So these are feeder plies in here, and then these become the repair plies out here. The laminate is sanded down so that a flat band of each layer is exposed, producing a step finish. That's the whole idea. And here at the bottom, you're going to have a backup ply that's going to help you out. Here you have a patch repair for sandwich construction. This core here is removed, and you then put a replacement core with a coarse plies adhesive. And then here you have the feeder plies, and then you will apply the extra plies. These top plies here allow keeping the inner plies bonded very well. Again, you're going to have repair plies in here. And so here's just a repetition of the picture above. You can also have a taper sanded repair where the replacement core goes here, and then you have these feeder plies here at the top. Again, a step sanded repair here at the top, as you see. You also can have a circular patch repair, like you see here. That's a very, very nice repair. The structural repair plies are here at the top. The ply here is a feeder ply, which is if you need it. And they're going to have a film adhesive that's going to help bring everything together. Remember that you want to keep a taper ratio. So this ply drop-off wants to be about 10 to 15 times the thickness. And then you're going to have this core that goes in here, bonded on all sides. An example of an Airbus repair patch looks like this. You have a rectangular repair patch like this, or circular repair patch, and then those go in here. The repair sequence is you have the puncture damage, take pictures, do an ND evaluation, try to understand what transpired, and then remove the damage, remove all the stress concentrations, and then taper, sand it down in this manner, and then you're going to then apply the replacement core. On the back end, you're going to have composites put in here, and then you're going to repair the second side here. Then you're going to put the repair plies and then some feeder plies. The idea is to bring everything together very nicely. If you can proof test the structure, that would be great. If not, you want to verify that repair using non-destructive evaluations, making sure that you have qualified the repair procedure very well. Typical repair procedures involve a power supply, compressed air to pull vacuum, thermocouples with a heater mat, all that, so you can do a heated repair, and this from Hexcel as an example. Here are typical bolted repairs where you could have these types of damage, and then what you do is you put plates on top that cover the repair area with bolts. The definition of potential damage sites is important. The definition of corresponding repair types is important. Here you can see a doubler lap repair to a stiffener foot in this area. And then here's a doubler lap repair through a damage, as you can see here. So it's important to apply doubler repair procedures whenever required. Here's an example of a passenger door damage. This came from the Boeing company, and so credit to them. But here you can see a repair procedure trying to repair a significant amount of damage. And so you want to fasten away from the damage, and then you want to have a bolt spacing that's good bolt spacing. So the stress concentration from one hole don't affect the next hole. And also, you want to keep all this metal well bolted into the composite with appropriate torques and things like that. A bolted repair. Here's an example of an Airbus wing box repair, which you can see here a patch with bolts, and there are circle regions here showing damage. But in general, you want to be able to implement a repair procedure of high confidence. It's not always possible to proof test a repair, but it is always possible to qualify the repair and ensure that the repair is a good one through coupon level testing, full scale testing, and using modeling to validate these repairs. So really, a bolted repair can be utilized to restore the capability of the structure to the original qualified capability. And so the decision-making process does involve analysis at times, and so that's why it's important that you validate it through coupon level testing that validates elements of the repair, and then a full-scale test of the repair to show that it's going to work in service. Because again, in service, it may not be always possible to proof test it. For example, of a finite element model trying to simulate a bolted repair. And so I want to make sure that your finite element analysis considers the doubler stress, the highest fastener load, and making sure that the percentage of load transfer is appropriate. You want to account for the stress concentration due to the corner of this repair. The door should include all the details. You want to calculate the maximum stresses. You want to determine the peak fastener loads, and then perform a fatigue assessment. You want to calculate the fastener shear, bending, composite bearing bypass interaction, and then determine the doubler bearing stress. You also want to validate the repair through testing. In this example, this repair was then bolted and then tested quite a bit. They took up, in this case, it took up 150% of the limit load. Here's a pause the video and feel free to go here to check it out. But in essence, you want to make sure the repair is robust. Here's an example of an Airbus repair. You have the fastener strength, the repair patches, and then you want to make sure you have you don't have buckling of the unsupported area, and then you want to then go in and bring everything together. You also want to make sure you have good bypass and bearing strength. So the bypass loading is in the x-axis. Y-axis, you have the bearing strength capability. You want to make sure that the bypass strength, which is a stress that acts in the far field and then acts such that it goes around the hole, and the loading that goes right through the hole through a bearing loading, that you're enveloped by the bypass bearing strength. These envelopes can be found through testing. You want to make sure that you're inside this envelope with a factor of safety of some kind. So I hope that's clear what I'm trying to say here. The Airbus methodology uses the user inputs, which could be geometry materials of the repair panel, fastener location, environmental conditions, and load. You will then generate the model and then extract the load distribution, and that will include the bearing load bypass loading at each fastener plate. And you will then take that information to then calculate both the joint margins, open hole margins, stability margins, and damage tolerance. The Airbus methodology for bonded repairs is very similar. You're really looking at the repair, bonded shear stresses, bonded shear strain, similar to the bonded joint lecture that we talked about, is in essence what we're doing here. So feel free to pause the video and kind of take a look at this Airbus methodology. Differences in material coefficient of thermal expansions can be an issue for both the repairs that should be considered in your analysis as well. Eccentricity may be larger in composite metal repairs due to the thicker gauges of the composite. Fastener failure modes need to be avoided. Here's an example of what the stress distribution looks in a step repair. These kind of you're gonna have the highest stresses at the edges of each of these ply drop-offs. And so you wanna be able to calculate the interlaminar stresses with a simple calculation and make sure you don't have an issue. Here's a recommended FAA bonded repair of aircraft composite sandwich structures that I recommend you go through. So feel free to pause the video there and download this particular paper. Interfacial failures have occurred if you can have a bad repair due to leaving a peel ply behind. You can have issues with if you have a bad repair, then you could also have failures, and that in this case there's humidity entrapped in the repair process. You also have ineffective surface prep or undercure of the composite, creating a patch failed repair. And there's types of damages. Looking at metals now, there's types of damages that also need to be considered. Corrosion, dent, galling, gouge, nick. Corrosion is a loss of metal from the surface by chemical action. And usually the corrosion is limited, so you want to find the root cause, mitigate it, remove the corroded regions, and then remove the material through mechanical means, and then analyze the structure. The dent can occur, so that's indentation of the metal. So you want to ensure that structural integrity is maintained, analyze for potential buckling and plastic deformation. You may need to reinforce the structure further. Galling is a breakdown of metal surfaces due to excessive friction between two parts. So you want to make sure that galling does not lead to crack initiation points. Gouge, you can have a groove in a metal surface from contact with foreign material under heavy pressure. And then nick, which is a local break or notch on the edge. Here's an example of repair. So here's the damage, and then you put the doubler down with these bolts. And so here's another example of having an area where from the back side you have a plate, from the top side you have a plate, and then you rivet the feeder in place. So here's another example. Here's a crack, and then you'll bring this piece in there and bolt it in. So you want to make sure that the stress concentrations combined with these stress concentrations by the crack tips are not going to make things worse, but in general, just keeping everything together. And feel free to pause the video and read everything here. I'm going to keep moving here to kind of show you the types of repairs. Another approaches that work really well if you have a crack is to drill a hole at each of the crack tips, and then don't let the crack, these crack tips, now that we have put a stress concentration that's more of a hole rather than infinite crack intensity factor, hopefully that crack will not grow any further. So the important thing here is to ensure that the crack will stay in place. And so, so here's all the repairs where you bring a piece from behind, a piece at the top, and then go ahead and bolt everything together. So, these are two different approaches that work really well. So here's an example of a damage that occurred at a stiffener. So in this case, you have to bring something that's molded to that shape and then bolt it through. Here's another example of damage where you're gonna bring another metal that's gonna come in here and attach through bolts. Here's an example where you have two holes and there's damage in between. You want to connect the two sides of the damage, and this is the load path right here. And so you're going to bring this in and bolt it in. So again, that's cracking between lightning holes. So you have to really consider that connection. Here's an example of a repair process for a pressurized section. In this case, you want to have a cedar material, and then you're going to bolt it through, making sure that the sealing action doesn't prevent any pressure leaks. Feel free to pause the video for any of these examples. Yet another example for stringers. So you have, again, a reinforcement from behind, and then at the top you bring it in like that. So again, in this case, you have a shape that matches that. And this is your fitter, and so you're gonna cut it apart, bring this in, and then bolt it through this reinforcement. Here's another example of a bulkhead. In this case, you have a crack, and then you bring this in, and you bolt it in, and this becomes your load path, this one right here. Yet another example of a wing spar rib repair. Here is an example of a patch. Another example of a patch if you have a damage like that. Here's another example of a damage, and then here you put some sort of reinforcement that has a shape. So again, all these needs to be qualified and verified that's going to work. If you have a leading edge issue, like a failure of some kind, you can cut it off and then bring this shape repair plate with a doubler behind, and then bring this into place and then bolt it in. Again, pause the video for any of these examples. So metal repair should consider the flaw assessment, fatigue assessment, bolt analysis, skin analysis, and demonstrate that the repair indeed restores the strength of the qualified configuration. You want to consider all the new failure modes that may have been introduced. Let me move into additive manufacturing. Very top level view, additive manufacturing refers to a process by which you can apply digital 3D design data to build up a component in layers by depositing materials. So all this was, this particular blade system was manufactured by depositing layers of material, and then basically through lasers, through heating, you get it all fused together. So this is like 3D printing. You're printing in 3D. In essence, you're adding material. That's why it's called additive. You're not subtracting material, you're adding material, and as a consequence, creating the shape of the material. This kind of technology can allow you to manufacture things you may not be able to do with other types of design. So say you have a sphere that's hollow inside. How can you manufacture that with other techniques? 3D printing allows you to manufacture such systems. Power bed process is one of the most common one, and it uses selective laser melting. The basic process is they use a layer by layer powder bed approach in which the desired component features are sintered and then solidified using a laser. So this is used widely in combustion devices. The advantages is that allows high resolution, fine features, sorry about that, including complex internal designs to be fabricated, such as cooling channels. The disadvantage is that you're scale limited and it cannot provide a solution for all components. Some notes that I want to talk about: the design and analysis need to consider the surface finish for internal and external features, because those surface finishes, if they're too coarse, can be initiations to failure. Internal passages may sometimes need to be oversized to account for the undersized hole, and the support material should be understood in the design phase, meaning if you don't have a good support material, the structure can crumble as you're making it. Placement of that support material is very important, and how you remove the material is equally important. The material properties can also depend on the print orientation. So the print orientation is critical. Whether you print it this way, from left to right or bottom to top, the material properties can vary quite significantly. So you need to consider part complexity, material, speed, part quantity, and cost. And just like when we discussed composite materials, you want to make sure that when you select the technology, you're not doing it because it's fancy, but because it's applicable to what you're trying to do, and is efficient for what you're trying to do. Printing approaches like sheet laminations. Sheets of materials are stacked and laminated together to form an object. The lamination method can be adhesives or chemical, ultrasonic welding, or brazing. The unneeded regions are cut out layer by layer and removed after the object is built. The strength of this approach is high volumetric build rates, relatively low cost, and typical materials used are paper, plastic sheets, metal foils, and tapes. And so I continue here going through the direct energy deposition, which is powder wire is fed into a melt pool, which has been generated on the surface. And so what you're doing there is the parts will then adhere to the underlying parts or layers by using an energy source such as a laser or electron beam. And so this is essentially a form of automated build-up welding. This is not limited by direction or axis. It's effective for repairs. Multiple materials can be used, and it has a high single point deposition rates, and you can use metallic wire powder with ceramics. The power bed fusion has alternate names. We have SLS, DMLS, SLM, EBM, and so forth. Powered materials are selectively consolidated by melting it together using a heat source such as a laser or electron beam. The powder surrounding the consolidated material acts as a support material for overhanging features. It can deal with high levels of complexity. The powder acts as a support material, and it can deal with a wide range of materials, including metals. The top issues are such as that AM can be manufacturing sensitive. It can be dependent on the processing of the part and the steps, like the way you make the part, in essence, the powder and everything else. Part strength can depend on surface finish and print direction, and material variability from one machine to another can be seen. Here's a paper that I recommend that you go and read. I think will be of great value to you. Pause the video and download it and learn something new there. Let me move to topology optimization. So topology optimization becomes very instrumental now, because if you can do 3D manufacturing of composites and you can make complex parts, then you can now use topology optimization to make parts that may not have been feasible before. So first, optimizing designs is important. You can save weight, remove non-stress regions. The pitfalls is that if you have a fairly good part that's robust, by optimizing the design, you may remove damage tolerance. So you may not have additional margins for defects. The designs will have less margins. So it may come up with unrealistic hard to inspect designs. So you may come up with a part that's very hard to inspect. And your designs could introduce stress concentration. So it's very important that when you optimize the design, you consider everything together. You're very careful about what you're doing, and that you don't blindly just make the part and it just pretends it's going to work. It's important to balance saving weight with how much structural robustness you need for a given design. And now that you have 3D printing, you can now do designs that, you can now design parts that may have not been possible before because you can manufacture them now. The best design is really determined by the parameters that are really chosen to describe the design of the system. And how do you do that? You define design variables, and these design variables play a key role in arriving to that best design. You can define an objective function, which can be the strain energy, the weight. You may have to specify constraints, and then you may have to also, really look for what the design variables are, which could be size, could be thickness, volume. The objective function should be expressed as a function of design variables. So here you have an objective function and you have some constraints, but you want to make sure that the objective function is a function of this design vector X. Your objective function could be cost, weight, displacements, natural frequency, mass. You can maximize natural frequencies or you can minimize them and so forth. The design process at very top level is that you apply the computer simulation, and you check whether you have minimized the design. If you have not converged to that solution, you improve the design and you continue until you get there. I'll give you a better view later towards the end, but the designer has to provide a design that is credible, meaning that you cannot modify areas that are affixed to other locations. So if you have attachment points, those points cannot be optimized because they're attached to other parts. You want to specify the materials, the factors of safety, the loads. You may have to subtract. The idea is to subtract the areas that have unnecessary mass because they don't conduce any stresses. You want to define interface geometries, enclosures, constraints. The software will generate numerous points of designs and display, and the idea is to select the best design that balances mass, strength, and stiffness. The general idea is that you start with an objective function f, which could be weight, and the general view is to use the gradient of the function f to determine, check the gradient of this f relative to the design variables, and the idea is that I am dropping to a minimum value, an optimal solution. And when the gradient reaches to a value of 0, you've gotten to an optimal value, and that's when you stop. It could be a local minimum. It may not be a global minimum. So you want to check your design over a large space. So typically in topology optimization, one approach is to minimize the total strain energy of the system. And the strain energy of the system is given by this formula. I won't go into this now, but U is the deflections of all the points. K is the stiffness of the system, of this finite element model. U is the vector of deflections of the whole, of each node, basically. So this U deflection vector contains all the nodal deflections. And so you want to subject that to the balance of equilibrium of the system. And so the idea is to determine whether I should have 0 mass or should I have a volume there. And you also want to constrain it so that you don't go to 0 volume either. So this is what this one is doing here. So here you have a cantilever beam subject to a load 10 by 20, and the question is how you optimize this design. So the idea of topology optimization is to put these constraints in, this objective function, this constraints in, and the idea is to use design sensitivity analysis to determine how sensitive this strain energy, in this case C, is sensitive to the variables of interest. In this case, the design variables are really the density. And so I'll take the derivative of C respect to the density and determine how this changes. And when this gradient approaches 0, then I know that I'm optimizing my solution slowly. The issue is that if I go from 0 to 1, I have a binary problem in which I could have convergence issues. And so interpolations maybe are better used to come up with the design. So in other words, I don't want to go from 0 to 1, but I want to linearly vary my modulus from 0 to 1, meaning with a scaling factor from 0 to 1. And the same thing with the Poisson ratio. That way, the design does not come checkerboard. Here is a solution to this design problem, and this is the most optimal design that will minimize this strain energy while reducing the volume to a minimum given a constraint, because you don't want to get 0 volume either. And here's another example of an analysis. I want to apply a 3-point bend loading. And the idea here is to start your analysis, apply the finite element process, and then do the sensitivity analysis, update the material density with the approach that we just discussed. And if it's converged, then you plot the results. And if it's not, you go back and redo it until I'm getting the sensitivity is actually converging and I'm getting the lowest strain energy possible. Then I can plot out my results, and typically you will kind of shape it to have a more defined boundary. So I'll go into the Abaqus tutorial. I'm going to have Lifu now walk us through this final tutorial.
Welcome to Final Element tutorial. Today we're going to learn how to use Abaqus to apply topology optimization. So here's our problem statement. This is a just a plate with 3 holes of diameter 5 millimeters, and the dimensions is listed here. This is 2 millimeter plate in thickness. So we can consider that as a plane stress problem, 2D problem. There's a force applied here with an angle of tangent equals to 3, and the value for that is 500 newtons. And our goal for this problem is to find the optimized geometry so that we can minimize the strain energy of the plate and subject to the reduced volume. Subjected to the reduced volume is greater than 60%. That means the remaining volume is smaller than 40%. So let's see how do we do that in Abaqus. Create a part. So this is 30 plus 30 plus 15, which is 75 in thickness. So we can make it about 100 here. So we can do either we do shell planar, and then here we create this geometry first. So 0, 0, and 75. The width is 15 plus 30 is 45. Now let's create a hole. Use the cut extrude and select this right length. And then our holes is at here, here, here. First mark the center first. So we can mark a center here and then use the dimension tools for that. This should be 7.5. And this is also 7.5. Similarly here and here. And yeah, this is 37.5. And now draw the circle. Let's draw the circle, all pointing downward, all pointing to the right. Use a dimension tool. This is 5. 5. 5. Oh, sorry, this is radius. So it should be 2.5. 2.5. Okay. Now let's go to property. So what the material we're going to use is aluminum. Since we're using millimeter as the unit, so we are going to include the material property in megapascal, which is 68.9 E3 megapascal. Poisson's ratio is 0.3. And here we do the shell element homogeneous plate. And here we apply a thickness of 2 millimeter. And then we assign the material. When everything is done, create a sampling. Now we need to do some partition to make the make the mesh easier. And use the partition tool, select the right end, and sketch the partition. First, we draw a circle here, similar for all the loaded region. This is for better mesh later. And use dimension tools to control the radius of, make it 5, which is double the radius of the hole. Then we draw a rectangle here and use the dimension tools to control that in 15, which is double the size from the center to the bottom. Similarly here. And here. And this distance should be, let's see. This should be 37.5 minus 7.5. So it should be 30. Okay, when all your geometry becomes green, it means they are constrained. Oh, I forgot one thing. To make the mesh looks better, you also need to create a vertical line here. See, here has a V, that means it's vertical constrained. Connect this two, and also connect this two. Also here. This three should be horizontal. By doing that, we make all the region like a rectangle, so it will be better meshed later. Then we create a reference point here. We are going to apply load on this reference point. So we create a couple. And we're going to fix all the degrees of freedom. Select surface and select the inner circle, which representing the bolt hole. So use kinematic constrain everything. And now we can apply the load. Oh, sorry, I forgot to create a step. So create a step, just static analysis. So in the load, create the load now, concentrated force. Select the reference point. And here we create a local coordinate, call it local coordinate, which is following this coordinate 1, 3. So your X origin, select this as your origin, and then select the point on your x-axis should be 1, 3, 0, and then sorry about that. That's actually wrong. So the origin, let's do 0, 0, and then the x-axis can be 1, 3, 0. And now you can see this is pointing to your force direction. And then just randomly enter anything. For example, 0, 1, 0. Now you have your local coordinate here. Select the local coordinate. And in your x1, we enter 500 Newton. And the other direction is 0. You can see your force is pointing to the correct direction. And now we create a boundary condition. In your initial, call it pin. So those two holes are pinned. And select the region, hold shift and select the other one. Use pin. Okay, so then we do the mesh. First change the mesh control for all the rectangular area. Make it to structure. And change the circular area. Make it to just leave it free. And sorry. So you cannot change the region near the hole. Now let's assign global size. So for optimization problem, we need to make it as fine as possible. Let's do 0.1. That may be a little bit too fine. Let's do 0.2 then. Now we can mesh. It should be pretty fine. You have 85,000 elements. And now in your tools, in your mesh element type, we have shell element reduce integration. So this is our element type. Now, before doing optimization, let's run the problem and see what do we get. Because it's a static problem, it should be pretty fast. Okay, so you will have the result. Let's do the edge free. You can see originally you have stress concentration on those points, and this part is mainly sustaining the force. But however, this part doesn't contain that much stress. But you can see that, for example, this corner and this corner are something we actually don't need. And we want to reduce and those blue things are something we want to eliminate. Those are useless to this kind of loading condition. That's why we do the optimization of the structure. So to do that, go to your optimization and create optimization task. and we select the topology optimization. And the region we are going to do optimize is everything other than the whole region. And we can freeze the this too. You can select. I will leave those circular region fixed. That means when you're doing topology analysis, those circular region will not be considered into your optimization problem. So doing dense, all other things you don't need to change. And now create optimization quantity. The one we need to use here is strain energy, single term for whole model, and strain energy. And we need another one is volume fracture. For the, actually, we only select the analysis part. So choose the volume. This is volume. And then we create our objective function, which is strain energy. And choose strain energy. And here we create our constraint. So our constraint is the volume fraction constraint. And we should have a fraction of initial value smaller, as I mentioned previously in the slides. The fraction is should be, the reduced volume should be more than 60%. That means the fraction should be smaller than 40%, 0.4. And here we create a geometry restriction. So we need some frozen area. Just call it fixed area, which are those small circles around the hole. Those are something we want to fix it, not include into optimization problem. Now, in your job, in the optimization process, create the process here. And everything, just leave it there. And you can choose to save the data every cycles. Let's say every 10 cycles. And definitely we need the last one. And maximum cycles, normally 50 is enough. So let's submit. So optimization process is like trial and error. It has some internal algorithm inside. Abaqus can actually show the process. Haven't started the first step yet. So our analysis has finished. You can see that your objective function reaches convergence, and normally your constraint will reach something close to the limit, which is 0.4. So let's see how does our result look like. So when you show the result, it asks you to rewrite the file into Abaqus file. So you can choose quantities to save. We just choose stress and displacement. And when this is finished, we can see the result. So this is our final design. And well, since we record, we only left the last one, so this is the optimize the result. So you can see that all this part, this corner part and this part are removed, and the rest is containing all the stresses. And here is thicker than this one. Since our force is mainly pointing towards the right hand side, that's why this part supports more load than this part. And that's how we apply the analysis. And optimization using Abaqus can help a lot of problems, and hope that you can enjoy this video.
Now we're going to try optimizing the problem using a different control volume.
Now let's see how to set up the optimization problem. So let's create a project, topology optimization. And the optimization region we are going to do is all the rectangular region. And all other things you can just leave it default. And now we create a variable we are going to control. So create the strain energy first. For the whole model, strain energy. And create a volume for the whole. The volume we cares are just the rectangular regions. So hold shift, select all of that, and then save volume. And then objective function here, and create, as we mentioned before, strain energy. Make sure this is the minimum design response value. And the constraint, as we say before, is the volume fraction. Choose the volume, and a fraction of initial value, choose 40%. Now we constrain the frozen area. The frozen area is all these rectangular region. So those are not included into the optimization. Now we can go to the job, and here optimization process, and then create the job. I already did it. So let's see the result. When you try to see the result, you need to convert it into Abaqus file first. So we ask you something. I already did it, so you can see the result now. The original result is like this. It may take some time, but it will end up with this one. Since the load is pointing to the right hand side, so the left hand, this bar is containing most of the strain energy. I can see this optimal design is not the best design. The shape is kind of weird here. So the reason for that is, although this minimizes the strain energy inside the structure, but your volume is not. If you see your job here, monitor, and then you can see the plot here. And this plot is showing your objective function versus the constraint. So you can see your constraint reaches almost the limit we set 0.4, while your objective function reaches minimum. But we want something that the volume is smaller, while we can sacrifice some of the objective function. That's why we change our objective function to, instead of only the strain energy, we here include a volume here, and change since the volume is way smaller than the strain energy, so we include a 10 in weight than the strain energy, see whether it works good or not. Besides, if you only do that, it may goes to some crazy value since you haven't set a limit for your strain energy. So we need another constraint, which for the strain energy, which should be dropped to lower than 50% of the initial value so that it won't blows up. Okay, when everything is done, we can go to the job, and here we create another optimization process. And I already did it, so you don't need to wait for that. And if you see the monitor, this is the result. You can see that the volume, which is the blue curve here, reaches the optimized point which we had previously, and then it decreased a lot this time because we set the objective function include the volume of it. And then now if you want to see the result, see it pop up a window asking you to combine that into the MATLAB result. We can select stress displacement here, and then it will convert into Abaqus file. And then we can see the result this time. So in this time, you can see that it looks way smaller than previous result. And you can see that you can even make it smaller by setting the constraint smaller and making the volume, let me go back here. You can even make this design better by making the volume weight larger or setting this constraint, which is 40% now, we can make it smaller, like 10% or something. So that's it about the optimization problem. Hope that you can learn something from about how to use Abaqus to do topology analysis optimization here. And thanks for listening to this video.
The designs that we came up with can be further improved. For example, there are some tight radii, and it will be very important to ensure that you improve the designs by making sure there's no stress concentrations. Have a great rest of your day.